Hello everyone and welcome to today's Power BI interview preparation session brought to you by Data Science with Harivansh. In this presentation, we are going to cover two very important and frequently asked Power BI interview questions. The first question explores the difference between two powerful DAX function all and all selected, which are both used to manipulate filter context in Power BI reports but behave very differently from each other. The second question focuses on how to optimize SQL queries within Power BI to improve report performance, a topic that is critically important for anyone building large scale data heavy Power BI dashboards. These are advanced level concepts that will truly set you apart in a Power BI interview. So let's break them down clearly and in complete detail. All versus all selected explained. Let's begin with the first question. What is the difference between the all and all selected functions in Power BI? Both of these are DAX functions that deal with filter context, the set of filters that are currently active in a report due to slicers, visual interactions, or page level filters. To understand the difference between them, you first need to understand what filter context means and why controlling it is so important in Power BI. In Power BI, every visual on a report page is influenced by the current filter context. When a user clicks on a slicer, selects a value in a chart, or applies a page level filter, the filter context changes, and every measure on the page recalculates based on those active filters. Sometimes, however, you want a measure to ignore certain filters. For example, when calculating a percentage of total where the denominator should always represent the complete total regardless of what filters the user has applied. This is exactly where all and all selected become essential tools. The all function is the more powerful and absolute of the two. When you use all in a DAX measure, it completely removes all filters from the specified table or column, and this means it ignores every filter without exception. It ignores slicer selections, it ignores visual level filters, it ignores page level filters, and it ignores report level filters. All essentially resets the filter context completely and calculates against the entire data set as if no filters existed at all. This makes all ideal for calculating grand totals, overall averages, or percentage of total calculations where the denominator must always represent 100% of the data. For example, if you write a measure like total sales equal to calculate sum sales amount all sales. This measure will always return the total sales across the entire data set, no matter what slicers or filters the user has applied on the report. The all selected function behaves differently and is more nuanced. Like all, it removes filters from the specified table or column, but with one very important exception. It preserves and respects the filters that the user has explicitly applied through slicers and visuals selections. In other words, all selected removes the internal visual filters such as the filters that come from the raw context within a matrix or table visual, but it keeps the external filters that the user has actively chosen through slicers and cross filtering. This makes all selected extremely useful for dynamic calculations where you want to show a value relative to the current user selection rather than relative to the entire dataset. For example, if a user selects the year 2024 in a slicer, a measure using all selected will calculate its total within the 2024 context, not across all years, making it perfect for calculating percentage of subtotal within the current visible selection. To summarize the key difference in the simplest possible terms, all ignores absolutely everything. It strips away every single filter and works with the complete unfiltered dataset. All selected respects what the user has chosen. It removes internal context filters but honors the user's slicer and selection based filters, making calculations relative to the user's current view. Use all when you need a fixed absolute total that never changes regardless of user interaction. Use all selected when you need a dynamic total that adjusts based on the user's current selections in the report. Excellent. Now let's move on to our second interview question, which is a very important performance related topic. How do you optimize SQL queries within Power BI to improve report performance? This question is asked frequently in interviews for senior Power BI developer and BI engineer roles because in real world enterprise environments, Power BI reports often connect to large databases with millions or even billions of rows. If your SQL queries and data loading strategies are not optimized, your reports will be painfully slow. Your dashboards will take minutes to refresh and the user experience will suffer significantly. Knowing how to optimize is therefore a critical professional skill. SQL optimization techniques in Power BI. There are seven there are seven key techniques for optimizing SQL queries and improving Power BI report performance. Let's go through each one in detail so you understand not just what to do, but why each technique makes a significant difference. The first technique is to select only the required columns. This sounds simple, but it is one of the most impactful optimizations you can make. When writing a SQL query or building a Power BI step in Power BI, many developers make the mistake of writing select all, which retrieves every single column from a table. If a table has 50 columns but your report only needs 5 of them, you are loading 10 times more data than necessary into your Power BI model. Every unnecessary column increases the size of your data model, consumes more memory, and slows down query performance. Always be specific, only select the exact columns your visuals and measures actually need. This reduces the volume of data transferred from the database to Power BI and keeps your model lean and fast. The second technique is to use filters to reduce data load. Rather than importing your entire dataset and then filtering it inside Power BI, you should push the filtering as far back as possible. Ideally, directly into the SQL query itself using where clauses. For example, if your report only covers the last 2 years of data, add a date filter in your SQL query so that only 2 years of records are imported, rather than importing 10 years of historical data and filtering it afterwards. The principle here is simple. The less data you bring into Power BI, the faster everything becomes, from data refresh times to visual rendering speed. The third technique is to index important columns in the database. This is a database level optimization that directly impacts how fast your SQL queries run. Database indexes are special data structures that allow the database engine to find and retrieve rows much faster. Similar to how an index at the back of a book helps you jump directly to the right page instead of reading every page. For columns that are frequently used in where clauses, join conditions, or order by clauses in your Power BI queries, such as date columns, ID columns, or category columns. Make sure those columns are properly indexed in the source database. A well-indexed database can make query execution times drop from minutes to seconds. The fourth technique is to use aggregations over row level data. When your report only needs summarized data such as total sales per month per region, there is no need to import millions of individual transaction rows and aggregate them inside Power BI. Instead, perform the aggregation at the SQL level by using group by with aggregate functions like sum, count, and average in your query. This dramatically reduces the number of rows being transferred from the database to Power BI. Power BI's aggregation tables features also allows you to pre-build aggregated tables in your model specifically for high-level summary visuals. So the engine can serve those visuals from the pre-aggregated table without scanning the full detailed data. The fifth technique is to optimize joins and avoid unnecessary ones. Joins are computationally expensive operations, especially when joining large tables together. Every unnecessary join adds processing overheated to your query. Before writing a query with multiple joins, ask yourself whether every joined table is truly needed for your report's requirements. Remove any joins that are not contributing directly to the output. Where joins are necessary, ensure that the columns being joined on are indexed in the database. Also, prefer inner joins over outer joins wherever possible, since inner joins are generally faster because they process fewer rows. The sixth technique is to use query folding in Power BI. Query folding is one of Power BI's most powerful and often underutilized performance features. When you apply transformations in the Power Query editor, such as filtering rows, removing columns, changing data types, or merging tables, Power BI tries to translate those transformations back into native SQL queries that are executed directly on the source database server. Rather than being processed by Power BI on the client side, this process is called query folding, and it means the heavy lifting of data transformation is done by the powerful database server rather than by Power BI's engine. You can check whether query folding is active for a query by right clicking a step in the Power Query editor and looking for the View Native Query option. If it is available and not grayed out, query folding is working. Always design your Power Query transformations in a way that preserves query folding, as it can lead to dramatic improvements in data refresh performance. The seventh and final technique is to use direct query carefully. Power BI offers two main data connectivity modes: import and direct query. In import mode, data is loaded into Power BI's in-memory storage engine, which makes visuals extremely fast to render. In direct query mode, every visual interaction, every click, every filter change, every slicer selection sends a live SQL query directly to the source database. While direct query is valuable for scenarios where data must always be real time and up to date, it can create significant performance bottlenecks if the underlying database is large or not well optimized. Because every single user interaction triggers a database query, if you must use direct query, make sure your database is well indexed, your queries are highly optimized, and you limit the number of visuals on each page to reduce the number of simultaneous queries being fired. For most reporting scenarios, import mode is the recommended choice for optimal performance. The overarching key takeaway from this entire slide in this Power BI report performance is not just about how you design your visuals, it is actually about how efficiently you retrieve and load your data. By selecting only the columns you need, filtering at the source, indexing your database, pre-aggregating data, optimizing your joins, Leveraging query folding and being strategic about direct query, you can build Power BI reports that are fast, scalable, and production ready even when working with very large enterprise datasets. Thank you.